Okay, so we have 4 important proofs in mathematics. These are optional. You can either memorize them or you can understand them. So to prove this, you can simply let P be x to the power m and Q be x to the power n. You can just choose any letters of your choice, and then expressing these two in log form, you have this one can be written as, to what power should I raise x to get p, and the power is m, like this. So this is the base, and then this is the power, and then this is the, I don't know if I should call it the product, depending on what sign is on m. And then you can do the same thing here. Log of base x of q is equal to n. So now we can start the proof by saying p times q is equal to, p is x to the power m multiplied by q is x to the power n. Then when you multiply these two, you have pq is equal to x to the power m plus n. And then now you can convert this to log form. As you can see, this is in exponential form. So you can just say log x is the base. In short, to what power should I raise x to get pq? And the power is m plus n. And then we know that m is this, and then n is that. So we have log x of pq is equal to, m is log x of p plus n is log x of q, which completes the product rule, and you're done. And then the same applies to the quotient rule of logs. So for this, you can as well just use this same data here. Let me just do this so that we don't waste a lot of time. So in this case, instead of multiplying, you can say p divided by q is equal to, p is x to the power m divided by x to the power n, which is q. And then we have p divided by, maybe we can just write it as p over q is equal to, when you're dividing indices with the same bases, you can just subtract the powers like this. And then now you can convert this to log form. So this one will be log, the base is x, this we have. So in short, to what power should you raise x to get p over q? And the power is m minus n. So now getting back to this part rather, we know that m is log x of p, so this will be log x of p, then minus n, this is log x of q, and you're done. This is the quotient rule as required. And then for part 3, we can use this same thing here again. Let me just use this small space. This is a short proof. For part 3, we have log x of p to the power n is equal to n log x of p. So now you can just raise p to the power, p is x to the power m, so you can just raise it to the power n and still using this information. And then after you do this, you know that p is x to the power m, so this will be x to the power m, then raised to the power n. Then after this is the same as x to the power m n, and then this side we have p to the power n. And then now, looking at this and this and that, of course we don't need this part anymore. You can just convert this to log form now. So you can say log x. To what power should you raise x to get p to the power n? And the power is mn. Then going back to this, we know that m is log x of p. Let me just write it like this so that it's much easier to see. So this is log x of p to the power n is equal to n. M is equal to, by the way, this n has nothing to do with this. It's just some random letter I used, so don't substitute it with that. So m will be log x of p, and you have completed the proof. Last one. This is equally useful, especially in IB mathematics, A-level mathematics, and other higher level mathematics. So when you have a to the power log a of x, and this is equal to x, in short, every time you have a raised to the power log a, as long as these two are the same, then your answer is just x, whatever this is. So to prove this, we can just introduce log a on both sides. To the power log a of x, and then log a of x. And then you can use the third rule, this one here, the power rule, to drop this one, to write it as a coefficient. Then you have log a of a is equal to log a of x. So now, to what power should you raise a to get a? The power is 1. In short, log a of a is just a 1. So we have log a of a. The 1 is understood. We don't really need to write it down. Then this is equal to log x of a. So as you can see, we have this is equal to that. So that means x is equal to that, which completes the proof.